Welcome to the deep dive. We're jumping straight into something really cutting edge in artificial intelligence
Oh,
today.
yeah.
Composable meta reasoning components. Forget AI just doing tasks. We're talking about AI that can, well, think about how it should think, how to do it most effectively.
Exactly. It's a big step. Makes AI potentially much more adaptable, more efficient.
So it's kind of like a two-part thing.
You could say that. First, there's the meta reasoning itself. AI getting strategic about its own problem solving, not just, following a script.
Okay.
And second, composability, which is all about building that intelligence from smaller, reusable bits like thinking modules. Snap together the right tools for the job.
Right, right, like cognitive Legos. And for our deep dive today, we're using a report, Composable Meta Reasoning Components Define.
It's a solid one.
Well,
Draws from both AI research and cognitive science. Really gets into the weeds.
yeah, it does. So our mission is to kind of unpack that, understand how breaking down AI thinking into these flexible parts could lead to, well, smarter AI. Cut through the jargon.
Sounds good. Let's start with the basics then. What is meta reasoning? Because it bridges how we think about our own thinking and how we design AI.
Okay, yeah, let's start with the human side. Cognitive science. Like when you're stuck on a puzzle, you don't just try random stuff usually. You might have a hunch, right? A feeling of knowing. Or maybe you realize, okay, this approach isn't working, gotta switch gears.
That's metacognition.
Yeah.
Your brain monitoring itself.
Exactly. And that connects to ideas like dual process theory, right? System 1, fast thinking, system 2, slow, deliberate stuff.
Yeah, and meta reasoning helps us decide which system to use or when to switch. Those little internal feelings, this feels right, or wait, something's off. That's all meta level control.
It even affects like how long you'll keep trying based on if you feel it's solvable.
Right. And what's really interesting is how that human stuff is inspiring AI now.
How so?
Well, in AI, the big challenge is often efficiency, achieving goals with limited time, limited memory, limited computation.
Sure, finite resources.
Exactly. So it's not just about getting the right answer, but getting it smartly. Meta reasoning lets the AI look inward, analyze its own algorithms, its own process. It's reasoning about its internal operations, not just the outside world.
Okay, so it's like self-monitoring for the AI. What can it actually do with that capability?
The report lays out a few key functions. First, just monitoring. Is it making progress? How sure is it about its steps? Is it detecting errors? That kind of ongoing assessment.
Like internal feedback.
Precisely. Then there's control or regulation. Based on that feedback, it makes decisions. Do I need more processing power here? Should I try a different algorithm? Or, crucially, when should I just stop thinking and give the best answer I have right now?
So it manages its own thinking effort.
You got it. It's like an internal governor.
Okay, what else?
Then you have strategy selection and discovery, choosing the best tool from its toolkit for the current problem, or maybe even, figuring out a new way if the old ways aren't cutting it.
Ah, so it can learn new strategies too.
Potentially, yeah. And finally, resource allocation. Just intelligently deciding where to spend its limited computational budget time, memory, processing cycles for the best possible outcome.
Okay, that makes sense. So we know what it does. How do researchers actually build this, formalize it?
Good question. The report mentions a few approaches. There's meta-level rationality, basically asking, was the thinking effort worth the potential improvement in the answer?
Right, a cost benefit for thinking.
Exactly. Then there's bounded optimality, which just acknowledges that even the meta-reasoning has limits and costs. You can't spend forever deciding how to decide.
Makes sense.
You also hear about value of computation, or VOC, that's the AI asking. Is more thinking likely to significantly help, or should I just go with what I have?
So weighing the cost of thinking versus the expected gain.
And finally, meta-level Markov decision processes, or MDPs. This frames the what computation to do next as a sequence of choices, kind of like how reinforcement learning agents learn actions in a game. It can learn the best meta-level actions over time.
Okay, interesting. So that covers meta reasoning. Now let's bring in the other piece, composability. You mentioned software engineering.
Yeah, that's where the idea really comes from. In software, it's about building big, complex systems from small, independent, reusable bits, like Legos, as you said.
Right.
Each piece does one thing well, connects easily to others. In AI, it's applying that same idea. Building complex intelligence from these independent, maybe even interchangeable components leads to what we call a composable architecture.
So what makes a component composable in this AI context? What are the key features?
Well, the report highlights a few things. They need to be modular and self-contained. Each one has a clear job, works on its own.
Okay.
They should be autonomous, doing their task without needing constant hand-holding. They interact through well-defined interfaces, like the Lego studs, so they connect predictably. Importantly, they should be loosely coupled, meaning changing one component doesn't break everything else. You limit the ripple effects. Ideally, they might be stateless, handling each input fresh, though managing state is sometimes necessary. And finally, standardization helps different components play nicely together.
And the payoff for building AI this way? What are the big wins?
Oh, quite a few. Reusability is huge. Use the same component in different systems. Scalability, easier to upgrade parts without redoing the whole thing. Much more flexibility and adaptability, swap components in and out for new tasks.
Sounds like it makes maintenance easier, too.
Definitely. Maintainability improves because you can isolate problems. Development can be faster. Testability is better. Test each piece alone. Better interoperability. And ultimately, it can be more cost-effective and future-proof.
Okay, standard software benefits. But how does this really apply to AI, which feels messier, more dynamic than typical software?
That's a fair point. In AI, composability isn't just about clean code. It's a way to manage the sheer complexity of intelligence. It helps structure how different cognitive functions, maybe different models, interact.
So it helps organize the AI's internal mind.
Sort of, yeah. And it helps tackle real-world complexity. Imagine an AI dynamically pulling together different reasoning components based on the situation it encounters. That's key for flexibility. It even kind of lines up with theories like the language of thought, complex thoughts, from simpler building blocks.
Plus, maybe makes it easier to understand what the AI is doing, more transparent.
That's definitely a hope. If you can see the components and how they connect, it might make these complex systems less of a black box, easier to debug, maybe even trust.
Are there any tricky bits when applying this software idea to AI? Any unique challenges?
Yeah, a couple of nuances. The goals can be different in AI. We might be aiming for cognitive flexibility, not just code reuse. And the whole stateless ideal from software. That can clash with reasoning.
How so?
Well, reasoning often depends on state, like what the AI currently believes or the history of its computation. So AI components might need more clever ways to handle this internal state compared to simple software modules. It requires careful design.
Okay, got it. So we have meta-reasoning thinking about thinking, and composability building with modular blocks. How do they merge into composable meta-reasoning components?
Right. The core idea, as the report frames it, is taking those composability principles, modularity, interfaces, reuse, and applying them directly to the meta-reasoning process itself.
So instead of one big control system for thinking.
Exactly. Instead of a monolithic controller, you break down that control layer into specialized, potentially reusable components. Each handles a specific bit of the meta-reasoning job.
Ah, okay. So you might have one module just for monitoring performance.
Yep. And another one whose job is just evaluating certainty. Maybe another dedicated to detecting when things go wrong, like a failure detection module.
And others for choosing strategies or allocating resources?
Precisely. Separate components for strategy selection, resource allocation, maybe even one that triggers learning or repair mechanisms when needed.
And the composable part means you can mix and match these meta-level skills.
That's the key. The AI system could dynamically assemble the right set of meta-reasoning tools for the current task. Simple problem. Maybe just basic monitoring.
But for something complex.
For something complex or novel, it might bring in more sophisticated components. Deeper monitoring, maybe comparing different strategies, a meta-level planner to manage thinking time strategically. It fits this idea of a meta-level architecture.
Where the knowledge about how to control reasoning is itself modular and explicit.
Exactly. Much more flexible than just hard-coding the control flow.
This sounds incredibly interdisciplinary. Who's working on this stuff? Which field?
Oh, absolutely. It pulls from everywhere. Obviously, core AI, rational agents, decision theory, resource management. We've talked about cognitive science providing inspiration from human metacognition. The boom in large language models, LLMs, has spurred a ton of work here. How to make them better reasoners, how to get them to choose strategies. Robotics needs this for adapting to messy real worlds and handling failures.
Sure, robots bump into things.
They do. Multi-agent systems, MAS, look at how multiple AIs can coordinate their meta-control. And then you have computational logic and meta-programming, which provide the formal tools to actually reason about computation.
Wow, that's a lot of different perspectives. Does that cause any friction? Like, are they all speaking the same language?
That's a major challenge, actually. The report calls it the heterogeneity problem. Different fields use different words, different formalisms for really similar ideas. Like an LLM researcher might talk about prompts for guiding reasoning, while a robotics person talks about specific software modules for failure detection and repair. Both are doing meta-level control, but the language is totally different.
So we need better translation between fields.
Yeah, or unifying frameworks. Things like the IM-ONTOL ontology mentioned in the report aim to create a common ground, a shared vocabulary, to help bridge these gaps. It's crucial for progress.
It really feels like AI is leaning more heavily on cognitive science lately, like using it as a direct blueprint almost.
Definitely seeing more of that. The report notes this trend, using concepts from cognitive science, not just as analogies, but as direct inspiration for AI architectures.
Like building AI modules named after cognitive functions.
Exactly. We see proposals for LLM systems with components explicitly called, self-awareness, monitoring, evaluation, meta-reflection, or frameworks inspired by dual process theory. There's a sense that human strategies for managing thought might be really valuable for AI.
Where did these ideas even start? What's the history here?
Well, the basic idea of separating control from object-level processing goes way back in AI. Then came key work, formalizing meta-reasoning as a decision problem, the value of computation stuff.
Right.
Meanwhile, cognitive scientists were figuring out human metacognition. In practice, meta-reasoning ideas were used early on in things like planning and search-managing algorithms, choosing strategies.
And more recently, with LLMs.
Yeah, huge surge there. Techniques like meta-reasoning prompting, MRP, where the prompt tells the LLM how to reason. More structured things like meta-chain of thought, multi-chain reasoning. Also, the whole idea of reflective systems, AI reasoning about itself, maybe modifying itself, has deep roots, and composability helps enable that. And formal logic folks have used meta-interpreters for ages to analyze programs.
Okay, so how does this translate into actual systems? What do these architectures look like in practice?
We see several patterns. Hierarchical architectures are common. A meta level controlling an object level, simple enough. In multi-agent systems, that control can be centralized or decentralized.
Okay.
Then you see pipeline architectures, like in computer vision maybe. Meta-reasoning components watch the data flow and tweak parameters of different modules in the pipeline.
Adjusting things on the fly based on performance.
Exactly. There are also modular reasoning frameworks. MRKL is a good example. A router sending queries to different expert modules, like an LLM or a calculator. The router itself is doing meta-reasoning.
Choosing the right tool.
Yep. And finally, lots of agent architectures, especially in robotics or planning, have explicit modules for meta-tasks. Monitoring plans, detecting failures, triggering repairs.
Can you give us some concrete system examples? Let's start with the LLM ones.
Sure. Meta-reasoning prompting, MRP, you give the LLM a prompt that says, okay, first, analyze this problem, then pick the best reasoning method from this list, then solve it.
So the prompt guides the meta-reasoning.
Right. There's also a proposed Bayesian meta-reasoning framework for LLMs with explicit modules mimicking human metacognition, self-awareness, monitoring, evaluation, regulation, meta-reflection, memory. Quite ambitious.
Wow.
Meta-chain of thought, MetaCut, tries to train LLMs on the structure of good reasoning, inspired by that dual process idea. Multi-chain reasoning, MCR, uses one LLM, a meta-reasoner, to look at multiple reasoning attempts from another LLM.
Ah, like getting multiple opinions.
Kind of. It analyzes those different chains of thought and synthesizes a better, more robust answer from the good bits. And meta-prompting looks at abstracting prompt design, making it more general. Recursive meta-prompting, RMP, even explores having LLMs design their own prompts.
Okay, that's fascinating. On the LLM side, what about outside language, robotics, planning?
You've got systems like HYDRA. It's designed for robots to detect unexpected things, novelties, and update their world models so they can replan effectively.
Adapting to surprises.
Exactly. And various robotics architectures for failure detection and repair. They often link high-level planning, like hierarchical task networks, HTNs, with sensors, and have a dedicated meta-reasoning bit that diagnoses failures using a predefined list or taxonomy, then triggers repairs. Some even use reinforcement learning to learn new repair strategies.
Learning from mistakes.
Going back a bit, Meta-AQUA was influential. It learned introspectively while understanding stories, using special patterns to analyze its own reasoning traces and figure out what it needed to learn next.
Interesting. Any others?
Microsoft Research explored using RL as a meta-reasoner for modular software, dynamically configuring components in, say, a vision pipeline to optimize overall performance. And in logic programming, meta-interpreters are classic examples, programs reasoning about other programs, analyzing structure, controlling execution.
Could you maybe walk through a quick scenario or two, show how these components might interact?
Sure. Let's take that complex math problem for an LLM. Using MRP, the first step isn't solving, it's analyzing.
Hmm.
The LLM reads the prompt, identifies the problem type, checks its list of reasoning strategies, and maybe decides, okay, tree of thoughts looks best here. Then it invokes that strategy.
Okay, so a selection step first. What about the robot example, HYDRA?
Right. Robots assembling IKEA furniture, following its plan. Suddenly, there's a drop tool blocking the way wasn't in the plans. Its plan inconsistency monitor flags a mismatch. The novelty determination component confirms, yep, this is new, unmodeled. Then the model repair component kicks in, updates the internal PDDL plus model, the representation of the world, and actions to include this obstacle. Now the planner can generate a new path around it.
Detection, confirmation, model update, replan. Got it. One more. Maybe that MCR one.
Okay, the tricky trivia. Director known for earthquake movies, also directed a Dwayne Johnson film.
Brad Payton, San Andreas.
Exactly. But an LLM might generate multiple reasoning chains. One gets it right. Another might focus on disaster films generally and go off track. A third might link Dwayne Johnson to other directors. The MCR meta-reasoner looks at all these chains, sees Brad Payton, San Andreas, appearing consistently in the plausible ones, maybe cross-references filmographies, and synthesizes the correct answer, filtering out the noise.
So it consolidates the reliable parts from multiple attempts. Very clever. These examples really help. So, summing up the potential upside, what are the big promising benefits here?
Flexibility and adaptability seem key. Being able to pick the right strategy, adapt to new stuff like HYDRA does, makes the AI less brittle.
Right. Not stuck in one mode.
Exactly. Then there's efficiency and resource management, optimizing that thinking cost versus quality trade-off, avoiding wasted computation, allocating resources smartly. And modularity helps with scalability. Think Meta AI's scalable memory layers, SMLs, using modularity for scale.
And robustness, reliability.
Yeah, definitely. Detecting and recovering from errors, like in the robotics examples. Handling unseen tasks better because they can adapt. Potentially better accuracy, like with MCR.
Yeah.
And the modularity should help with maintenance, debugging, maybe even explainability down the line.
It sounds almost too good to be true. What's the catch? What are the big hurdles?
Oh, there are plenty.
Yeah.
It's not easy. Implementation is tough, designing good components, defining those interfaces, making sure they integrate smoothly, especially if they're from different sources. That's complex engineering.
And debugging must be a nightmare.
It can be. Debugging emergent interactions between components, figuring out which component is responsible when something goes wrong, that's hard. Then there's the computational overhead.
The cost of thinking about thinking.
Right. Meta-reasoning isn't free. You need to ensure the benefit outweighs that cost. Calculating the true value of computation precisely is often intractable, so you rely on approximations, heuristics. Scalability of the meta level itself can be an issue.
Any deeper theoretical problems.
Yep. That heterogeneity problem, lack of standard terms and frameworks. Figuring out the optimal way to compose components for any given situation is a huge challenge. Getting formal guarantees about behavior is really difficult. Just defining what good reasoning is can be tricky.
And controlling the meta level itself.
That's inherently hard too. It's often a sequential decision problem under uncertainty. Coordinating meta control in multi-agent systems adds another layer of complexity. When should it stop thinking? How does it handle switching context between reasoning and meta-reasoning? There's even this idea of the metacognition paradox. Could thinking about thinking actually interfere with the main task?
Food for thought, definitely. Okay, so how does this relate to other buzzwords like modular AI design, meta-learning, reflective systems? Are they all the same thing?
Good question. They're related but distinct. Think of modular AI design as the broad principle. Composable meta-reasoning is applying that principle specifically to the control layer, the reasoning about reasoning part.
Okay, so meta-reasoning is one application of modularity. What about meta-learning?
Meta-learning is about learning how to learn better, usually across tasks, improving future learning. Meta-reasoning is about making smart choices within a task at runtime. They're complementary, though. You could meta-learn good meta-reasoning components, for instance.
Makes sense. And reflective systems.
Reflective systems are agents that can reason about their own internals, often to improve themselves. Meta-reasoning is a core mechanism that enables reflection. You need to reason about your state to reflect on it. Composability helps by making those internal states more distinct and accessible for reflection. Reflection is maybe broader, including self-modification.
The report had a table summarizing this.
Yeah, it breaks down the focus, mechanism, timescale, and goal for each. Really useful for keeping them straight.
Okay, so as we start to wrap this up, what's the big picture takeaway on composable meta-reasoning components?
I think the core idea is that combining composability and meta-reasoning offers a path towards AI that's smarter, more adaptable, more efficient because it can manage its own thinking process using these flexible specialized parts.
Tailoring its approach.
Exactly, moving beyond rigid algorithms.
But as we said, lots of challenges remain. It's not solved yet.
Not by a long shot. Huge
Yeah.
potential, but significant hurdles too. The report outlines lots of open research questions. Component design, integration, control, learning these components, verification, making it work in multi-agent systems. It's an active, exciting area.
What's needed moving forward?
Well, progress on standardization would help.
Mm-hmm.
More research into learning-based control for the meta level, exploring hybrid architectures, better debugging tools, and crucially, continued collaboration across AI, cognitive science, robotics, logic, all those fields.
It really does feel like a fundamental shift is underway in how we think about building intelligence.
I think so. Giving AI the ability to reason about its own reasoning, that could fundamentally change how these systems work, how we interact with them, moving towards something more truly adaptive.
A fascinating prospect. Definitely something to keep an eye on.
For sure.
All right, on that forward-looking note, we'll bring this deep dive to a close. Thanks for joining us.